So starting out today with a problem. I got lots of problems. You see me limping today. I run most mornings and I twisted my ankle. So I think I'm fine, but I'm limping a little. So, but I think I'll live, at least for a while longer. But like, as you know, I like to go around. But anyways, so I got this problem here. So methane plus water produces carbon monoxide and 3 hydrogens. We have methane with 25.5 liters at 732 torr and 25 degrees Celsius, and we have water at 22.8 liters, 702 torr, and 125 degrees Celsius. And we're making 26.2 liters of hydrogen at 760 torr and 0 degrees Celsius. So here are the things you need to know. That should be Kelvin. So ideal gas law, PV equals nRT. There's R, there's Kelvin, there's atmospheres to torr. This is the same as before, theoretical yield, percent yield. So what is the percent yield of this equation here? So it's a limiting reagent problem, and you're given an actual yield, and now you have to determine what the percent yield is from these data. So, like I said, you can't forget anything. Everything carries through to the end. Is anyone stuck? Has no idea where to start? Nope. Okay. And I'm going to sit down because I'm in pain. Ugh. So I went ahead and showed you the solution for methane. Methane gives you 1 mole methane. How many moles of hydrogen would that 1 mole of methane make? What does the balance equation say? 3. It's a 1 to 3 ratio. So that 1 mole of methane would make 3 moles of hydrogen. So looking at this, is methane CH4, is that the limiting reagent? No, it's not. Why not? So water's got lower volume, has lower pressure, and higher temperature. And comparing that to, so PV equals nRT, N is the moles. So it is directly proportional to pressure and volume and inversely proportional to temperature. So that means that the lower volume, lower pressure means less moles. And then since it's inversely proportional to temperature, the higher temperature means lower moles. So it's definitely, the water is definitely the limiting reagent. But if you didn't know that, you can calculate out the number of moles and then figure out that way. But I set it up for you safely because I know it's not the answer. So then you have to figure out the number of moles of water. Then you have to multiply it by 3 to get the moles of hydrogen that you should get. That's your theoretical yield. And then you got to look at the moles of hydrogen that are produced. Take the moles of hydrogen that are produced divided by the theoretical yield to get the percent yield. That's how you solve the problem. Hey, the plus side is at least I don't have to calculate a molecular weight on this one. Is anybody stuck? No one's stuck? Just working? Okay. I didn't write everything down. It says you get this and it takes that. That's the product of the molecule. So it's percent even. I mean, I'm not good with carbon monoxide. Those hydrogens are products of the right.
Right. So.
Yeah, carbon monoxide.
So. That makes sense. Okay.
Okay, so 702 divided by 760 times 22.8 divided by R 0.8206 divided by 398. So that's that. And there are 3 moles of hydrogen for every mole of water. So we multiply that by 3. You get 8.93. That's exactly what. Following? You have any questions?
I am following. I was just curious. Where did you get the 1.17? Did I just not read your writing right? The one for the NH2.
Yeah. So that one there. Well, 760 divided by 760 is 1. 26.2 divided by R.08206 divided by 273.
Yeah, that's what I got to. But I'm just wondering. I'm not seeing the. Is this NH2?
And N is number of moles.
Oh, okay. I'm saying I'm looking for some chemical that doesn't exist.
Yeah.
I'm following.
Yeah.
Thank you.
So it's 1.17 divided by the theoretical yield, which is 1.93. So it's
Yeah.
60-ish, 61%.
Yeah,
Yeah. Okay. All right.
Thank you.
Isn't that wonderful? You have to remember everything from every previous topic. Okay. Anybody have any questions for this? Looks like everyone is kind of getting it. Rough way to start a Tuesday morning, huh? Or this is Wednesday. Jeez. No wonder my Tuesday is going terrible. It's Wednesday. All right. So next thing I'm going to talk about is kinetic molecular theory. So that's what the ideal gas law is based off of, is kinetic molecular theory. With this, I guess I can erase this. I was just doing an example. What's your favorite fast food? What's your guilty pleasure? Someone give me a really guilty pleasure. Jack in the Box. Okay. What food item at Jack in the Box? Spicy chicken sandwich. Okay. How many calories are in Jack in the Box's spicy chicken sandwich? Oh, there's 1.8 miles away on Lower Main Street. Thank you so much, Google, for that. Okay, it's 550 calories. So, does that mean that every single spicy chicken sandwich you buy has 550 calories? No, right? You probably have something that looks like this. You have a distribution of that. So let me compare that to temperature. So remember, temperature is an average kinetic energy. Does that mean that if you have, so right now the temperature is about 25 degrees. So we are at about 298 Kelvin right now, plus or minus 2 or so Kelvin. can't really tell right now. So does that mean that every single gas particle has the same kinetic energy? No, it doesn't. We have its average kinetic energy. So just like kinetic, so just like with the calories in some of our favorite fast food item, temperature. So temperature is kinetic energy, and a bar over it means mean or average. So the average kinetic energy is a temperature. And so kinetic molecular theory is based on these postulates. Do you know what a postulate is? A postulate is something you take without proof. So it's a mathematical term. So here are the postulates for kinetic molecular theory. The size of a gas particle is negligibly small, and which means that the particles themselves are small. So atoms are small. So this is a pretty good approximation postulate. The average kinetic energy of a particle is proportional to temperature in Kelvin, which makes sense. That's a definition of Kelvin anyways. And then the collision of one particle with another or the walls of a container is completely elastic, meaning there's no attraction whatsoever. So where this kind of reminds me of, I used to work at Bath and Body Works in Victoria's Secret, and we did a lot of marketing, of course. If you guys want to know what Victoria's Secret really is, it's marketing. Marketing is Victoria's Secret. So, and actually, it's interesting also that marketing is changing. Victoria's Secret is losing money. Well, they're not going under, but they're not making as much as they used to, because of my generation, good old millennials. So some of the culture is changing, but with Victoria's Secret, a lot of times you look at the big thing back in the 90s and whatnot were the models, and they tried to capture what the most perfect source of beauty was. Like what's the perfect woman looks like? What does the perfect man look like? It's also interesting with beauty, it's changed over the years. So if you look at the Renaissance, so the most beautiful thing were men. Men was the male form, the 18-year-old ripped male form was the most beautiful thing. So if you ever seen Michelangelo, so all of his sculptures, all of his paintings are basically men. So and they're specifically 18-year-old athletic men. So David, of course, that's obvious. So there was a sculpture he made of Moses. It was basically an 18-year-old dude, ripped, with a beard and horns on his head. There's a mistranslation that Moses didn't have horns on his head. But then you looked at women, they were basically ripped 18-year-old men with breasts. So if you look at the ceiling of the Sistine Chapel, that was the most beautiful thing. Men were beautiful, women were disgusting and ugly. And now we've had to switch. It's interesting with contemporary society, we've had a turnaround that the young female is now the epitome of beauty, and men are disgusting. So it's interesting that how culture can change. But what does the most beautiful, perfect man or woman look like? We have that in art. If you can call Victoria's Secret posters art, or Michelangelo, you can certainly call Michelangelo art. What is the perfect gas like? Imagine your ideal gas, if you will, right? So the ideal gas is one which the particle that makes up the gas doesn't exist. All the faults that you have as a gas are just not there. There is no particle to the gas. The gas has a volume, but no size itself. Then the average kinetic energy is the temperature. And that's the definition as well, but that's an easy one. And then there is absolutely no attraction whatsoever. Anytime there's a collision, so the gas particles actually have no mass, they don't have any size, when they actually do collide, they have no attraction to each other. And so this is your ideal gas. The ideal gas law is actually a mathematically derived equation from these postulates. So the ideal gas, unfortunately, doesn't exist. And I talked about temperature. Remember, we talked about the, was it spicy chicken sandwich? Is that right?
Mm-hmm.
You have a distribution. Well, let's talk about velocity, well, temperature. So here are a series of gases all at the same temperature. So the y-axis is the number. The x-axis is the velocity. And so I guess it'd be better to say speed, because velocity can be both positive and negative. But the magnitude of the velocity here, and notice a couple things. So oxygen, 32 grams per mole, nitrogen, 28 grams per mole, water, 18 grams per mole, helium, 4 grams per mole, hydrogen, 2 grams per mole. That the heavier gases have a narrow distribution, the light gases have a broad distribution. And the other thing to notice, you have gas particles that have zero velocity, a very small number, meaning you have all these gases, they're flying around, they're banging into each other. But let's say, for instance, you have two, they hit each other, and one bounces off, and this one's not moving, but it gets hit again. So at any given time, you have a very small percentage of gas particles that are not moving at all. And you could argue, well, they're at absolute zero. But, I mean, overall, the gas is not at absolute zero. Just a few of the particles are not moving at all. But most of them are moving. And you also have the peaks. See these peaks here? These peaks here, these also correspond to what we'll learn later on today. I hope we get to this, is what's called the root mean squared velocity. So what is the root mean squared velocity? Well, it's the square root of the mean of the velocity squared. So why do we square velocity? Because velocity can be negative. How do you make sure something is not a negative number? You square it. And what number that you square is not negative? So all real numbers, right? If you square an imaginary number, it might turn negative. But a real number, if you square it, it turns positive. And we deal with, at least with magnitudes in chemistry and physics, it's only real. You can't have imaginary atoms or imaginary velocity or something like that. So do imaginary numbers exist in science? Yes, they do, but they deal with periodicity, like sine function is imaginary, for instance. But that's a different topic for a different class, I suppose. Okay, so you square the velocity, get rid of the negatives. You take the average, the mean of that, and you do a square root of that, and that's the root mean square velocity. And we'll talk about this later on. That turns out to be a different equation. 3RT over molecular weight. Okay, so let's talk about with the same temperature. So these are three gases. Well, sorry, same gas, all the same temperature. So y-axis is relative number, x-axis is molecular velocity. So, or at least the magnitude of the velocity. And notice here is at 0 degrees Celsius, 273 Kelvin. Here's at 1,000 Kelvin. Here's at 2,000 Kelvin. What happens at cooler temperatures? There's a real narrow distribution. As the temperature increases, the distribution of velocities increases. So, and I mentioned this before. Later on, well, this is next semester, but we'll talk about kinetics and chemical reactions and activation energy. So right now, this textbook is burning. It is burning at this temperature. It's burning very slowly, but in 1,000 years, this textbook will be a pile of ash. Which means that there's a really, really tiny amount of gas particles in air that has enough energy to break down well, it's mostly sugar. It's mostly cellulose. So there's enough energy in there to break down the paper. If you raise it to 2,000 Kelvin, so let's see here, what would that be in Fahrenheit? That would be pretty hot. That would roughly be around, so at least double that, around 4,000 to 5,000-ish Fahrenheit. So that would be like a Bunsen burner temperature, maybe even hotter than that, maybe like a welding torch. How long would this textbook take if I took a welding torch to it? I don't know, depending on where I put the torch. I don't know, a minute, if I was lucky. Why does it take so short? Well, if this is the energy, there's a little less than half of the gas particles can react. So, which means you're going to have, and look at this tiny slice versus this amount, there's a lot more chance of chemical reaction going on in that case. So, by probability, it'll burn much faster at 2,000 Kelvin. Not surprising, right? Not a very surprising thing. So, that's what temperature is, and that's the distribution of temperature. Okay, I guess we're done there. And I mentioned before about the root mean squared velocity. So root mean squared velocity and average kinetic energy there. Here's a derivation for it. I don't like derivations, to be honest. So, but here is the so what. The root mean squared velocity is equal to the square root of 3RT over the molecular weight. And what is weird about this one is that you have to use the units R. So R is, I told you before, it's the Boltzmann constant times the Avogadro's constant. There are actually two constants there. But R also has the value of 8.314 joules per mole Kelvin. And the units will become important in a second. Let me show you. So let's calculate the root mean squared velocity of oxygen molecules at 25 degrees Celsius. So, and we got to use the equation 3RT over molecular weight. So, but in doing so, what is that sound?
That was me, sorry.
Oh, okay. Never mind. You're good, Phil. Okay, but so we put 3R is 8.314 joules per mole Kelvin. Temperature is 298 Kelvin. All over molecular weight, 0.032 kilograms per mole. And a square root, that's the same thing as taking something to the half. So that's the. So let's look at the units. So kelvins cancel, 1 over moles cancel. So unit-wise, the equals with the D, that means dimensionality. We have a joule over a kilogram to the 1/2 power. So a joule is a kilogram meter squared per second squared. That's the dimensionality of a joule. So the way I always remember this, force is equal to mass times acceleration. So force, that's Newton's second law. This is physics. You don't have to worry about it for this class. So the force in a Newton is a force, is a kilogram times acceleration. Acceleration is the second derivative of a displacement. So displacement is usually x in physics, but meters, length to meters, divided by, so then the second derivative with respect to time, so it would be over time squared. So it's kilogram meter per second squared as a Newton, and a joule, the energy is a Newton meter. So it's the force of a Newton over the length of a meter. So a Newton is a kilogram meter per second squared, and a meter is just a meter. So then a joule, a Newton meter, is a kilogram meter squared per second squared. So, and if you've never had physics, that's okay. And if you're wondering, you will always get this given to you as far as dimensionality is concerned. So a joule over a kilogram, this is a kilogram meter squared per second squared divided by a kilogram, so 1/2, which is a meter squared per second squared, right? The kilograms cancel. It's a meter squared per second squared square root, which is meters per second. So taking the square root of meter squared over second squared is meters per second. So then you just have to put this into your calculator. Does mine do square roots? I don't want to do that one. Okay, so if you put this all in, you get 482 meters per second. And the trick for this one is to use 8.314 joule per mole Kelvin for R. Don't use 0.08206. The units are different. See that it's liter atmospheres versus joules. And then make sure the molecular weight is in kilograms and not grams. And if you do that, you'll get the root mean squared velocity being 482 meters per second. So, so this is at 25 degrees Celsius. That means that the oxygen molecules, and we're about 25 degrees Celsius, that means the oxygen molecules flying around this room have the peak of their distribution being at 482 meters a second. Some are moving faster, some are moving more slowly, but on average, they're 482 meters a second. You know what? What's also interesting? That's faster than the speed of sound. So why aren't we having sonic booms right now? Why aren't all these oxygen molecules creating mini sonic booms, and we're hearing popping noises all over the time, constantly? Are they there and we just can't hear them because we're so used to them? Well, remember the nature of sound. Sound is a longitudinal wave, and it's carried by the matter. So this is the matter itself. The oxygen is not big enough. First of all, it's not big enough to break the sound barrier because, and the other thing is the wave is carried through air, which is the medium itself. So it's not going to create little sonic booms. But if you have a jet that goes through this, it'll make a sonic boom. And those are loud. Have you ever heard a sonic boom before? They're loud. So, interesting stuff. We'll recap with this one. I guess I did a recap. Why not have another recap? We can have tons of recaps. Root mean squared velocity. We apply the equation square root of 3RT over molecular weight in kilograms. So put in 3R being 8.314, temperature 298 Kelvin over 0.032 kilograms per mole. And we look at the dimensionality. It turns out to be meters a second. So we get 482 meters a second. Questions on how to do this one? And by far, the most common mistake is using the wrong value of R. The second most common mistake is using grams instead of kilograms. So if it makes you feel better, when I give you the equation in the next test, I tell you to put it in and I say M is in kilograms per mole. I don't tell you to use I don't say which R to use, but.
Your joule equals kilogram. What is that equation? What does that all mean?
This one here?
Yeah.
That's what a joule is.
Yes, I realize that, but what do the letters mean?
Kg is kilogram, M is meter, S is second.
Second. Okay, thank you.
So energy is mass times distance squared divided by time squared. I don't know way you could read that. It's a physics concept. And I happen to be a physical chemist. Any other questions? Yes, please.
How did we get to 482?
3 times 8.314. That's about 24 times 298. So that's 24 times 300. So oh crap. And then divided by 0.032. So let me do this in a calculator. It's just here. I'll do it in a calculator.
I figured out what I did, sorry.
2 times. I can't. Where's my? Oh, where is it? There we go. Ah. Like that? Other questions? All right, so next thing, talk about gas particles. So the distance between a collision is the mean free path, and that's how far it can go. And it can collide with other gas particles that collide with the wall. Meaning you have a gas particle, and so imagine you have a gas particle in a box. It wouldn't be a box, it would be like a smooth container, but hits the wall, and it usually makes a sound like pew. So it goes pew, 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 pew. At least in my mind, that's what it goes. So, right? So it bounces around, and as it's bouncing around, where does this thing end? Wait, it goes there. I can't see where this thing ends. Oh, it goes out. I see. But the idea, though, a gas particle, it's flying around, bouncing into things. And among other things we talked about before, the pressure from a gas also exists from these collisions. So if you get hit by one gas particle, not a big deal. But if you get hit by like a mole of gas particles, you can get into that. But then also with that, if you increase the temperature, you increase the speed, which means you have more collisions. And the collisions have more momentum, because momentum is mass times velocity. So you have more collisions, and each collision has more strength. So that's the thing with pressure. So that's how gases really move around. And with this, we have the idea of effusion. So this is Graham's law of effusion. And the Graham's law of effusion, it's the rate of gas A over the rate of gas B is the square root of the molecular weight of gas B over the molecular weight of gas A. Which, another way of saying it, the heavier the gas is, the slower it effuses through something. So if you see here, this picture here, you have the mean free path. Remember, the gas particles, pew, 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 just running around, and occasionally one flies out. And what Graham is saying is that the rate of this effusion, the rate of this gas leaving, is 1 over the square root of the molecular, I guess I should use the rate of something leaving is 1 over the square root of the molecular weight. Because the RMS velocity is 3RT over molecular weight, square root of 3RT over molecular weight. For the same temperature, 3RT is the same for each. And so the molecular weight is what's different. Meaning, like here in Hawaii, right, we never really have to, we don't have to do the tricks you do in the mainland. If you live on the mainland and you own and drive a car, you have to add more air to your tires in the winter, and you have to take air out of your tires in the springtime because the tire pressure changes. Here, we don't have to do that. But every once in a while, you have to add air to your tires. And why do you have to add air to your tires? Well, because there's little tiny cracks in your tire. And over time, it just diffuses. So the gas particles will escape. Same thing with helium balloons. You ever bought a helium balloon before? I mean, now the metallic ones, they float for a long time, but like after a week, they start to get kind of droopy, right? The helium eventually does escape. And the reason for that is because it effuses. It effuses through tiny little holes in it. If it was a perfect container, it wouldn't escape at all. But, I mean, do we have containers like that? We have containers close to that. We have them in, like, the International Space Station. So, but we don't have that. We're not going to have that level of precision for like a happy birthday balloon or get well balloon, right? So, or even a tire. But the tires nowadays they seem to be pretty good. I rarely have to put air in my tires, at least. Okay, so that's effusion. And so what? Why do we care? This is also how we enrich uranium to make nuclear weapons and for nuclear power plants. So let's do this. An unknown gas diffuses a rate that is 0.462 times that of nitrogen gas. So meaning we had two things. It was 0.462 times that of nitrogen gas. So this would be your rate of your unknown over the rate of N2 equals the square root of, the rate of the unknown is equal to square root of the molecular weight of nitrogen all over the molecular weight of your unknown. So, and this is 0.462. So how do we solve this? We square both sides. 0.462 squared is equal to the square root of, oh no, I don't got the square root, sorry. Molecular weight of nitrogen, which is 28 grams per mole, all over, I'll just give it X. I like X as my unknown. And X equals 28 divided by 0.462 squared, then that equals 131 grams per mole. So that means our unknown gas is got a mass of 131 grams per mole, and it's probably xenon. Xenon is 131 grams per mole. So yes, you can use this to figure out unknowns, but also more important, the more important application for this is nuclear enrichment. Did I go really too fast? Or?
What is that formula with 0.462 squared equals 28 grams per mole? What is that?
So, okay. So rate of A over rate of B. This is Graham's law of fusion. That's this.
Right. So we just found out rate.
So rate of A, and so and our A is equal to our unknown. And B is nitrogen. And the rate, also the rate of the the rate of unknown over rate of nitrogen, this is 0.462, which is given in the problem. So applying Graham's law of fusion. So rate of the unknown over rate of N2, this is 0.462, which is the molecular weight of nitrogen over the molecular weight of unknown. The molecular weight of nitrogen is 28 grams per mole, so 14 times 2. And the molecular weight of our unknown, I just gave this the value X. I said it was X. So this is our X. So I squared it to get rid of so I took both sides of the equation, I squared it to get this. Solve for X and get 131. Okay. So I can read body language, you just have to give me the body language to work with. I'm not on the autism spectrum. No, apparently people on the autism spectrum can't read social cues and body language. And the so what for this? This is how we enrich uranium. So this was figured out by Glenn Seaborg, and this is how we got the first material to make nuclear weapons, at least. So what Glenn Seaborg did is he reacted uranium with fluorine to make uranium hexafluoride, and then used centrifuges. And this is interesting right now, although we haven't been talking about in the news that much. It has to do with Iran making nuclear weapons. So a civilian nuclear power plant. So if you dig up uranium from the ground, it's the fuel that runs the power plants and nuclear bombs. It's 235, uranium-235. So, and you dig the uranium from the ground, on average here on Earth, has about 0.7% uranium-235. So, and you can enrich it. So here in the United States, we typically enrich it to about 3 to 9%, depending on the type of nuclear plant we have. We have 106 nuclear plants in operation, and we have 106 different designs for nuclear power plants. So we don't do our nuclear energy very well in this country. But now in Iran, they have uranium that's enriched past 20%. So then the Iranians say, oh, it's for civilian use. So either Iranians hate money and they're galactically stupid, or they're making nuclear weapons, or they're making something that will fit in a small container, like nuclear subs, for instance, like a civilian nuclear power plant. The core of it, depending on if it's a 0.5 gigabyte plant, it's probably about four times the size of this desk. Whereas a nuclear sub, the core is probably about this big. So why are they tiny on a nuclear sub? Because space is an issue. Yeah, they use weapons-grade plutonium, or weapons-grade uranium. So, but in a civilian plant, who cares if your core is this big or as big as this room? Who cares? You have tons of space, so you don't have to worry about space. And besides that, it's safer. If you have less fuel, more spread out, it's easier to keep cold. So it's safer and it's cheaper. So Iran is definitely, they're trying to make nuclear weapons. So that's one of the, or they're trying to make nuclear subs. So, but they, I guess they do have a port. And I guess that's better than North Korea. North Korea has nukes, but they use plutonium. And plutonium is much easier to make than enriching uranium. And also plutonium makes better nuclear weapons. But the weapons that North Korea has are not that good.
The missiles over here yet.
Well, they could, but they can't aim them.
They've been trying.
Yeah. So the last bomb that they made, they said they made a hydrogen bomb. I don't think they made a hydrogen bomb. I think they made what's called a fusion boosted device. That's if you put tritium. If you pack tritium in a nuclear bomb, then it does that. But it's still not big enough. They're not doing So a uranium bomb, you need to have 50 kilograms of very high enriched uranium. And the simplest design is if you have a cylinder with a hole cut out to it, and you have another cylinder. If you shoot a cylinder into this one, then you get what's called critical mass, which is at 50 kilograms. The thing explodes. So that was the nuclear bomb they dropped on Hiroshima. The Trinity explosion, the first nuclear weapon in Los Alamos, was a plutonium weapon. And the difference with plutonium is you only need 5 kilograms. So, and 5 kilograms of plutonium is about the size of a softball. So, but you have to put explosives on the side. You have to compress it down. What's called the rate of spontaneous fission is too high. So if you have 2 plugs, if you had like a 3 kilogram plug and a 2 kilogram plug and shot them together, the bomb would fizz, what do they call it? It would react too quickly and it would explode
at a lower yield. It would be a very dirty explosion too, but it wouldn't be a very big explosion. You have to compress it down, and you have to do it properly. Actually, it's not classified. The amount of the critical mass is not classified, surprisingly, but the way that they make the explosion is classified. So, and North Korea hasn't mastered that. It's a really, I mean, they got it. They can make a pretty good explosion, but like if they blew up a one at Costco, it might take out Krispy Kreme, but we would get irradiated here, but the blast wouldn't hit us. So it wouldn't be a very big explosion. But I still wouldn't want one coming our way, of course. But yeah, well, as scary nuclear weapons are, I'm not going to go through this example. I think there's not really any point. The answer is this one. So how much does it take to enrich uranium? The point of this one, it's really hard to do, and it takes a lot of energy and effort. Back in the Cold War, when we were we in the United States, let's see here, we have about 6,000 nuclear devices now. We used to have 30,000. So through treaties, we've greatly reduced our nuclear arsenal. And most of them are plutonium. And plutonium is interesting because you literally have to make it one atom at a time. And we have tons of the stuff. So we've disassembled most of our nuclear weapons. We keep the plutonium in Livermore and Oak Ridge. Livermore in California, Oak Ridge in Tennessee. So we have a stockpile of plutonium there. And so we could make more bombs if we wanted to. But some of the nuclear weapons we have are so ridiculous. They have nuclear grenades because it's 5 kilograms. 5 kilograms is 11 pounds. So you could throw, it's like a shot put. So, you could throw a nuclear grenade with a yield of like 5 to 20 kilotons. But, if you threw a grenade like that, the furthest you could probably throw it at like a shot put is like 40 feet. What hole are you going to duck under while that thing goes off? So they actually had those in case Russia invaded Europe. If they would wait till a bunch of tanks would come over, then they would set off the grenades and blow up the tanks that way. And they also have nuclear tipped artillery devices too. So at least those shoot a couple miles away. They're still scary stuff. All right, let's talk about things that are less scary. I used to be a nuclear physicist. That's why I know a lot about nuclear weapons. But when we had the nuclear scare last year, I remember I got scared. Ooh, that was scary. Anyways, okay. So let's talk about real gases. I'm not going to test you on this stuff. This stuff is no longer fair game. So here is the ideal gas. The ideal gas has a volume of about 22.41 at 0 degrees Celsius and 1 atmosphere of pressure. And if you look at this compared to other gases, and if you look at the closest to ideal gas you can get is helium. And helium is also the smallest atom. You'll find that out later. It's the smallest atom. And hydrogen, surprisingly, has a little bit of repulsion there. It's a little bit bigger. But this is what I mean by this. At this temperature and pressure, most gases are relatively ideal. And it's true. Most gases do act relatively ideal. When do gases not act ideally? When they're under high pressure or low temperature. High pressure, because the ideal gas law is based off the fact that gases themselves have no volume, but if you're under really, really high pressure, there's a lot of material there, and then the size of the particle, the size of the atoms, becomes an issue, and that makes the volume a little bit bigger than it should. And then also cold temperatures. So when things move more slowly, they get stickier. So think of something like acetic acid. So acetic acid has a has the oxygen and then a hydrogen, and they have a bond between them. And so when they're going around in space, they actually like to hold hands like this. The hydrogens and the oxygens like to kind of hang out together. So if you have two gas particles, and if they meet, they can kind of hold hands, and then they dance around holding hands. The problem is, here you have 2 moles of gas, and now it's like you have 1 mole of gas. So when you have the cold temperature, what happens is the gas particles start to attract to each other, and then they stick together, and then it seems like the number of moles that there should be there is less than it actually should. And then there's the van der Waals equation. So van der Waal tried to get around that. So got around that for the particle volume and then the attraction from the temperature. So that's the van der Waals equation. And here are the van der Waals constants. And the truth be told, this is a bad way to do it. So there are much better ways to do this. If you take engineering classes, they might mention the van der Waals equation, but they'll say, yeah, this is a terrible idea. You should never do this. There's a better, so one of the ways, so PV equals nRT, you can do PV equals Z nRT. This is the single easiest way to do it, and you can put a term in the front. This is called a lump sum approximation. So lump sum approximation. You do this a lot. So is anyone here want to be an engineer out of curiosity? We don't have, we got 1. Okay. Not too many engineers. Have you ever studied friction before? Has anyone ever studied friction? So friction, if you study friction, friction is equal to some coefficient times the normal force. So like if it's kinetic friction or static friction, you have some term times the normal force. And that's not what the friction is. Okay, so like when they say friction, like if I rub my hands together, this is kinetic friction because it's moving, and I can feel my hand get warmer. And they're saying like, okay, there's some sort of the surface of my hand rubbing against this surface, we give it a coefficient. And is that really the friction? And the answer is no. The friction is if you looked at my hands like this, and then you looked at each atom and the electrons and the attractions and repulsion of each atom and electron in my hand here. Now I move it a little bit and you recalculate it. If you did this sequentially for each motion, you could calculate out what the friction is. And the computer power to do that would be, immensely astronomical. Instead, what you can do is you can do a lump sum approximation. You're going to say, you know what? We're going to measure this in the laboratory, and we're going to find something that works, and we're just going to plug all, say, all right, all these variables that we really know what's going on, we're going to kind of say, you know what? This kind of works, and we're going to go with it. And that's what's called it's called a semi-empirical model, so sorted experimental model. So taking data and taking a bunch of numbers and then running them and finding out something that works. And that's what the van der Waals equation is. It's the same idea. It was a semi-empirical model. It's an elegant one, but this works better. The lump sum approximation. It works better. It works really well for friction. I mean, no one really says that's not really what the friction is. So, but you see this so often. Once you see this, these lump sum approximation, they pop up everywhere. At least if you study engineering, like heat transfer coefficients, for instance. So there's lots of heat transfer coefficients. It's all just, you know what? We took all this stuff, we threw it in one, and hey, it works, and we're just gonna go with it. And we know it works because our cars run, right? So and then we use lots of heat transfer in cars and AC units and these kind of things. Okay, and even better. So even better if you don't want to use equations, there's lots of real data. There's something called the Perry's Handbook of Chemical Engineering. It's a book about this thick. It's like this thick and it's like this big, so it weighs about 15 pounds. And there's tons of data in it. You can find real data. And one of them, for instance, they call it the Cox charts, the COX charts. They're just pages and pages of data on gases, and they're also in logarithmic plots. You can find real data on these. So you don't have to calculate anything. You can just look up the data itself. There's also a saying that a day in the library will save you a month in the laboratory. So a lot of times, you can just look things up. But of course, you have to know what you're looking for. You can't just go like, oh, maybe someone's already had my problem solved. If someone already solved your problem, then they probably wouldn't have hired you. Okay, so real gases are not on the tests. So we only deal with ideal gases. But why do I talk about them? For two reasons. Number one, to make you think, okay, that's what ideal gas is. Ideal gas, this is actually a derived equation. So it's a mathematical relationship. It's an ideal gas. It's something that's it's like string theory. String theory is mathematically beautiful kind of thing. So, but ideal gas, there is no such thing as an ideal gas, but we use it as a model. So, but then also real gases, because if you go on and learn other things, you have to worry about real gases. But the truth of the matter is, unless you're a chemical engineer working at a plant, or if you're like a rocket scientist designing engines, you probably don't really have to worry about real gases that much, to be perfectly honest with you. Or I guess there's some other things. If you're doing things with supercritical fluids, like if you're decaffeinating things, or maybe you're making some really cold beer, then you'd have to worry about ideal gas or real gases. Or maybe you're just used to using the equipment and then you don't need to know the chemistry behind it. Who knows? Okay, so am I done with this? Okay, yeah, I guess I'm done. We're 4 minutes to the end. If no one has any questions, I'll probably just end it here, and then we'll talk about thermo next time on Monday. Anybody have any questions? No? Okay.
Were you going to give us our test back today? Do you have the option of giving them a test?
Oh, I'm gonna give you guys a test back on Monday.
I beg your pardon.
Yeah.
Thank you. I thought it was Wednesday.
Wednesday is the last day that people can take the test. I usually give them a week. If you want your test back, I can give it to you now if you want.
Either way.
Yeah, it's up to you.
And then we have until like the 31st.
Yeah, the first. Take a retext. Yeah.
Great.
I haven't put it in the testing center yet.
Yeah, right, because those other people had to take it. I've
Yeah.
forgotten that.
I know I don't have to do that.